everyone, and welcome back to our Calc 2 videos. We are just now starting Chapter 8. Chapter 8 is going to take everything you've learned so far about integration and various integral techniques and on it. And you're going to learn a lot more techniques to, work with some of those integrals you weren't able to integrate prior. To get started, we're just going to start writing down kind of what we already know. So this is a nice little review of everything we've done on integration. So call, if you don't have, you're integrating any constant. In this case, we're integrating 1. It's just going to be your x plus your c. These are all indefinite integrals. Of course, your power rule for indefinite integrals. This power rule, as you know, can be applied to positive. It can be applied to fractions where the variable with the exponent is in the denominator, because you can rewrite those as negative exponents. And of course, it can also be applied to any type of radical, because those also can be written as exponents. So basically, anything that can be written as an exponent can use the power rule. So often we can rearrange what we have to get these exponents in order to use the power rule. And of course, we know our e, and let's suppose we have e to any coefficient of x. So the integral of e is just itself, and then of course if you have a coefficient of x, you would divide by that, and that comes out of that u sub process. All right, let's keep going. Integral of 1 over x dx is our natural log of x. And of course, all of your trig functions, I am only going to put sine here. And the integral of sine, of course, is the opposite of cosine x, plus all other trig, and we can actually add hyperbolic functions to this. So you do need to know those. Inverse functions we really didn't do a lot with, but I will say the one that comes up quite often is your 1 plus x squared, 1 over 1 plus x squared dx. So no, if you're going to, not memorize any other inverse functions, please know your tan. That is a very common one and is used often. Now, of course, with all of these, you've also used what we call the u sub technique. So far, you have your basic integrals along with your u sub technique. Now, there are variations on these that really help, and these are our algebraic. We'll call these our algebraic manipulations. These algebraic manipulations are very useful. It's just quite often, the hardest thing is to recognize them. So I'm going to go through just a bunch of examples to help recall or introduce some new algebraic manipulations. Of course, if you have any polynomial of any size, it could be, I have a binomial here, we could have a trinomial or any size, and it's all over a single monomial, a single term, you can always break those up, right? 2 over x to the 8th plus 3x squared over x to the 8th dx. In breaking those up, we can then simplify and put them as so they're no longer fractions, so we can use our negative exponents in this case. So that one's going to end up being 3 over x to the negative 6. And again, there's one of those cases where it very nicely turns into our u sub. Just don't forget when dealing with negative exponents, you increase the exponent. So when you increase 1 and add 1 to negative 8, you get 2x to the negative 7. Now, we often don't leave our exponents like this. We can go ahead and put them back. Okay, so that's one technique that you are familiar with. Also, with trig functions, and we're going to expand this a little greater in section 8.3. You can take a basic trig function like tan that you don't have an integral for, and you can simply rewrite it as sine x over cosine x. That allows us to very quickly use our u sub. Recall when you're using u sub, and in this case, you know, if u is sine, you can get the derivative of sine, which is cosine. If u is cosine, you can get the derivative of cosine, which is sine. You allow the u to be in the denominator. That is important because your du needs to be in the numerator. Of course, that's negative sine x dx. When you look at that, oh, we need to add the negative, which means we need to balance that with the negative on the outside. There's our negative sine x dx. So this simply becomes the integral of du over u, or 1 over u du. It's the same exact thing with our minus sign on the outside. And that's negative ln u plus c, which equals negative ln cosine x plus c. Now this is kind of an interesting one because of our properties of natural log. Doesn't that also equal So see all that trig manipulation we did? In essence, the natural log, or the integral of tan x, is equal to the natural log of secant x, or the opposite natural log of cosine x. But again, utilizing the fact that when we're dealing with our logarithms, remember the fact that ln of x cubed equals 3 ln x. So that means whatever is outside, that negative 1 we have outside, can actually be applied as an exponent to what we're taking the natural log of, hence making it an inverse. So there you have something that you should probably remember from this point on, is that the integral of tangent is actually equal to the natural log of secant. Let's continue. Here's a kind of a new one. I don't know if you've come across this yet. So in looking at this problem initially, Well, you can't really break it up because you don't have that monomial in the denominator. You have a binomial, so you can't just break that fraction up like we did in the first example. You can't let u equals x plus 4 because the derivative is not x squared. Now, if you let u equal x squared plus 2x minus 1, your derivative's 2x plus 2. You can try to get that to manipulate to x plus 4, but here's why that's not going to work. You're going to end up with a du in the denominator, and that doesn't work. So, we're stuck. So you thought. Or we can bring back this old technique called long division. Remember long division? Well, what if I took x squared plus 2x minus 1 and divided it by x plus 4? So I'm going to move up my long division thing. Is it bringing back memories from pre-calc? Because we really didn't do much long division in Calc 1, but clearly we're going to do some long division here. So real quick, x into x squared is going to be an x term, right? Because x times x is x squared. Keep in mind with long division, the important thing is keep everything lined up. What do I mean by that? All x squares go here, x's go here, constants go there, all right? So what do we say? What do we need to multiply x by to get x squared? We need an x, so it's got to go above the x column, okay? Got to go above x. All right, x times x is x squared. X times 4x is plus 4x. We're going to subtract. Oh, that's a minus. That's a minus. So what's that going to give us? It's going to give us negative 2x minus 1. So what do we need? We need a minus 2. Negative 2x minus 8. Again, you're really subtracting. So that's plus, so we end up with 7. And how do we write those denominators? It's a positive 7, so it's plus 7 over x plus 4. So my integral went from x squared plus 2x minus 1 over x plus 4 to x minus 2 plus 7 over x plus 4 dx. This is something that I can now integrate because x is just, well, that's x squared over 2 minus 2x. And here I have a quick little u sub where u equals x plus 4 du equals 1 dx. The problem, of course, I have a 7 here. So for this to work, I need to get rid of the 7, so I need to multiply by 1 over 7. It removes the 7 here, so I get a nice integral and can use a natural log, but to remove the 7 here, I got to balance it by putting it back over there. So it ends up being plus 7 natural log of x plus 4 plus c. Okay, so here's a new algebraic manipulation technique, and it has to do with our natural log. Speaking of natural logs, okay, so here's a natural log problem I want to take a look at. To do this right here, which is ln squared of x squared, well, kind of like the sine function, that's ln of x squared squared. You know, in those trig functions, you can move the square to the outside. Now, the inside piece, because of our properties of logs, can become 2 ln x squared. Or, you know, 4 ln x squared. Okay? So essentially, I can start off by moving my 4 on the outside, and then I have ln of x squared over x dx. Now at this point I can do a quick u sub for ln x, right? Because du is then 1 over x dx, which I have 1 over x dx right here. So that lets me rewrite this yet again. As for integral, we'll take care of our boundaries for the integral in 1 second. U squared du. Now the integral, for ex squared, ln of x, ln of ex squared, well, that's going to be 2 times ln of v, which is just 2, right? The lower boundary was 1, and that's just ln of 1. Well, think about that for a second. E to what power equals 1? That has to be 0. So we're going to go from 0 to 2. Okay? Because we changed our boundaries. Well, we left them here. We changed them down here. So that's 4 u cubed over 3 from 0 to 2. So that's 4 thirds, 8 minus 0, 32 thirds. Okay? So there's a nice little natural log function. Let's take a look at another little algebraic manipulation. Example 5. And for this one, I want to integrate from 0 to 2 of x over x squared plus 4x plus 8 dx. So this one is a little bit more complicated because I'm sure you're looking at this like, I'm not even sure what to do. You can't do the division. You can't take x and divide by the denominator. That's not going to work. That denominator as it stands cannot be factored. This one really requires a lot of algebraic manipulation, but let's do it. It's a good one to have, and this way you can refer back to it if needed. You can refer back to your notes. And the idea here is I can't even really use u sub, because if you let u equal x squared plus 4x plus 8, you have 2x, which is great. You can turn that into a 2x, but you got 2x plus 4, and you can't just add 4. That's not going to get you anywhere. So here's what we're going to do. We're going to take this x squared plus 4x plus 4, or plus 8, sorry. Right now it's plus 8. And we're going to try to break it up by completing the square. What would need to be there? Move the 8 to the other side. So I got a perfect square trinomial that I can then write it as perfect square. Well, that's kind of easy. I can put a 4 here. I can put a 4 there as long as I also subtract a 4. So just bear with me on this one. If you put a 4 there, that's going to give you x plus 2 squared. Now I've used up to here. I still have minus 4 plus 8 plus 4. And you're thinking, well, I don't know where that's going to get me, but hey, let's try it. So integral 0 to 2 of x over x plus 2 squared plus 4. I'm going to show you right now where that gets you, because now if I let u equal x plus 2, my du is simply dx. No, I don't have to worry about that plus 4, except I have an x up there I need to deal with, but that's okay. Because when we do our u sub, we can u sub a lot of things. We don't have to just u sub what we're familiar with. So let's take a look. Well, my dx simply goes to du. That part's easy. I can change my boundary. If I plug in 0, I get 2. If I plug in 2, I get 4. My dx went to du. We'll do the denominator first. U equals x plus 2, so now I have u squared plus 4. And what is x? Well, come over here. X is simply equal to u minus 2. So u sub does not need to just work on one part of your integral. It could work on various parts as long as you're swapping out every x for a u. And that's what we did here. We swapped out every x for u. So now we're looking at, well, believe it or not, this is a little bit easier to integrate. But I still just can't let u be u squared plus 4. I need to do another u sub. I need 2u. I've got this u minus 2. That's not going to work. What I can now do is break it up. I can put u over u squared plus 4, and I can put 2 over u squared plus 4. So now we can do a u sub. It's kind of funny to call it a u sub, so let's call it something else like a g sub. For the first part, I could do, well, g equals u squared plus 4, so dg equals 2u du. So what does that give me? Oh, I got to be careful, because I can, well, here, let's do this as well. To make this a little bit easier, we will break up our two integrals. All right, we'll break them up. So they're two separate integrals. So this is the first one. And I have to once again change my boundary. So I have a 4 and a 2 on the first integral. So that's going to give me, well, 4 squared is 16. So that's going to go to 20. And 2 is going to go to 8. And I need 2u, so I got to put a 1/2 out here. And that's going to end up being 1/2 dg over g. Now, I can pull the 2 out of this one. So now I have 1 over u squared plus 4 du. And that remains our our inverse tan function. If you come all, let me scroll up for a minute. So inverse tan was simply x squared plus 1, but instead of a 1, we don't have x squared plus 1 in this case. We have our x squared plus 2, right? Because that would be 2 squared. So then let's rewrite the first one. We're not done with that yet. And using our inverse tan, well, I'll just write this down for a second. I rewrote the whole thing, sorry. Okay. So this one is just going to be 1/2 ln of g from 8 to 20 minus 2 times 1/2 tan inverse u over 2, and that one's going to go from 2 to 4. Again, not the easiest integral. I'm just showing you the and this is this right here is basically just using u sub on tan inverse. Okay, which says the integral of 1 over x squared plus 1 dx equals tan inverse. We just, instead of doing 1, we used the 2. All right. We can finish it up. You know, you have 1/2 ln of 20 minus ln of 8. This just ends up being yeah, so we get tan inverse of, and you plug in your 4 over 2 is 2. Sorry. The 2 and the 1/2, of course, cancel. Tan inverse of 2 minus a minus, so it ends up being plus tan inverse of 1, because if I put it in parentheses, it's going to be minus tan inverse 2 minus tan inverse 1, which is just going to be tan inverse 2. That's it. You can clean this up, of course. Watch. So we have 1/2. When you subtract, you're really doing 20 over 8. Okay. Oh, when is tangent equal to 1? Well, tan is equal to 1 when it's angle's pi over 4, so we can simplify that. And so we have, I don't know, 1/2 ln of 5/2 minus. Okay, so this is all correct. It's a crazy integral, but here's my point to you. Yeah, it can be done. Now, on a test, am I going to make you do that? No, I'm not going to make you do all that on the test. Any of the other ones are good for the test, but not particularly this one for a test. But in the lab, maybe, because you need to go through and understand, I can do all this algebra manipulation, I can do all this work, and can end up with a workable integral. An integral that, before I even learn anything in Chapter 8, I can fully evaluate. I will take a look at one more quick one, and then that'll be it for this video. So number 6. Let's do e. E over e to the 2x minus 4e to the negative x dx. All right, take a look. So here's something you can do with these e values, right? E over e to x minus 4 over e to the x. So one method of algebra manipulation is something you learned way back in intermediate algebra, a little bit in pre-calc, is reduce the complex fraction. Meaning we have complex fractions when you have fraction inside of another fraction. So go ahead, and the way we do that, the only mini denominator is this e to the x. So what I'm going to do is go ahead and multiply each term by e to the x. Basically, I'm multiplying the whole fraction by e to the x over e to the x, and then I distribute it because that's just 1, right? And then I take it and distribute it through each piece. All right, so let's clean this up. So that's going to give me forgot the x there. Apologize. That is an e to the x, not an e. E would be a constant. Okay, so let's take a look at, like I said, one more problem. My video cut off for a minute, so I'm not sure where I was with this problem, but let me write it out again. Hopefully it didn't go backwards. I missed a part of it anyway. What I want to do is e to the 2x over e to the 2x minus 4e to the negative x. So again, if this started and popped back, I apologize. Okay, one thing I want to show you is what we really have here is a complex fraction. Right? And you've learned how to get rid of and how to simplify complex fractions. Basically, we want to get rid of it so that we don't have these fractions inside a fraction. And essentially what we're going to do is take the common denominator, which is just e to the x, and we're going to multiply numerator and denominator by e to the x. So when you do that to the denominator, you actually distribute it through so it gets multiplied by everything. Sorry. And when I multiply it by everything, e to the 2x times another e to the x is going to give me e to the 3x. Same here. Minus 4, because my e to the x is gone. This, as you can imagine, helps a lot because you can see your u sub now. If I let u equal e to the 3x minus 4, because we always let u equal the denominator when we have fractions like this, then I'm going to get a 3e to the 3x dx. E to the 3x dx. What's missing? I'm missing a 3, so I need a 1/3 out here. So now I have 1/3 du over u, which is 1/3 natural log of u, sorry, plus c. Of course, you can't leave it that simple. Let's do 1/3 natural log of e to the 3x minus 4 plus c. Okay, and just showing you that's also the same as the natural log of the cubed root of e to the 3x minus 4 plus c. You should always put those absolute value signs, but if they're not there, it's not a problem. This answer is perfectly fine, but you need to recognize both of them. So this video, again, just give you a bunch of examples of kind of harder integrals that involve some difficult algebra manipulations, but these are integrals you can do based on everything you've learned up to this point. In the next video, we'll start some new integration techniques.